All right, we're going to take a quick look here at area between two curves. So our goal right now, we have these two graphs. This is just a generalized thing, just kind of show how this works. This is a graph of f of x and a graph of g of x right here. And we're trying to find the area of the region bounded by those two curves, which would be this region right here. Okay, so that's what we're looking for. Now, the idea that we're going to use for this, again, this is just kind of quickly showing the concepts behind this here. If I were to just sketch the graph of f of x, and going back to this real quick, you can see the intersection point here is x equals a, the intersection point here with these two graphs is x equals b. And if I were to just graph f of x, and if I were to just look at the area under f of x from a to b, it would include all of this area as well as everything below all the way down to the x-axis. And again, this is the graph of f of x that I'm graphing right here. To find this, we've discussed that before, you would find the integral of f of x from a to b. Okay, so that would just give you the area under f of x from a to b. Alright? And then what we would do, let's go and take a look if we would just graph g of x. So let's say here's a and b. Okay? And so this area right here would represent the area that is underneath, not this shaded region, but the area underneath that shaded region. Okay? This again right here is the graph of g of x. In order to find that area, we would just integrate from a to b of g of x. So what I'm going to do here is I'm going to think of, if I take this area, which again is this shaded area plus everything below, and subtract this area from it, I would just be left with this area right here. So that's which is what I'm after. So I could set up, basically that first integral minus the second integral, and that would leave me with the area that I'm interested in. Now, typically you'll see these combined together because just same idea. If you have an integral with multiple terms separated by a plus or minus, you can separate those into integrals. This time you can combine them. So this could just be written as the integral from a to b of f of x minus g of x. So, in general, the way I like to think of area between two curves would be, it's the integral of the top curve minus the bottom curve. So you can see, again, the curve that's on top here is f of x, the curve that's on bottom here is g of x. The limits of integration are just based here, went from x equals a to x equals b. That's, where the region lies between those two x values. And this will work if this area we're talking about is below the x-axis. If a portion is above, a portion is below, it always works. It's just the integral of the top curve minus the bottom curve. Okay, let's go ahead and take a look at an example here. So we're going to find the area of the region bounded by y equals 2 minus x squared and y equals x. So, first thing I'm going to want to do is to get a sketch of this region just to see what it looks like. This right here can easily be sketched by hand. And 2 minus x squared is just a downward facing parabola shifted up 2 units. So you can see I'm doing a very general sketch. The line y equals x goes through the origin and it has a slope of 1. So let me extend this down here so I can see where they intersect each other. Okay. So what I'm looking at here, this is the region right here that I'm looking at. That is the area that I want to find. So this graph right here is this guy, and y equals x is the line we're talking about right here. Okay? So just a moment ago we said, okay, if you're looking for the area between two curves, it's the integral of the top curve minus the bottom curve. So that applies here. It's the integral of the top curve, which is 2 minus x squared, minus the bottom curve, which is just x. Okay? Now we have to figure out our limits of integration, which are going to be determined by where the intersection point is here and here. So to figure that out, a lot of times it's calculator active, but we'll do this one without a calculator. To find where two equations intersect each other, that is just where they are equal. They share the same point, so therefore they're equal at that point of intersection. So let's set 2 minus x squared equal to x. We'll do that right over here. So 2 minus x squared equals x. To solve this, I'm going to move everything to one side so I can end up factoring it. I'd rather have the x squared be positive, so let's move to the right side. So we'll add the x squared, keep the x, and then subtract the 2. So that will factor into x plus 2, x minus 1, and then negative 2 and 1 are my intersections. Or where those are equal, which lead me to where my intersections are. So that right there, that intersection occurs at negative 2, this intersection right here occurs at 1. So that's going to be my limits on my integral. Okay? And now we're just integrating. This one's kind of a pain with the fractions, but let me show the antiderivative here. So the antiderivative is going to be 2x minus x cubed over 3 minus x squared over 2 from -2 to 1. Okay? And then at this point, you're just going to go ahead and plug 1 in for x. So it'll end up being 2 minus 1/3 minus 1/2. And then minus, then I'm going to plug -2 in for x, which will be -4 minus, I have -2 cubed over 3. I'm sorry, that's a cube right there. And then minus -2 squared over 2. So again, all I did right there is I took the 1 and I plugged it in first, minus, took the -2 and plugged it in. And right now it looks kind of ugly. That does simplify to 9 over 2. Okay? So if you need to practice simplifying that, you can go ahead and work through it, and you should be able to find a common denominator and simplify it down to 9 over 2. Okay, let's take a look at another example here, and this is one that we're going to go and use our calculator on. Now, the actual graphs of e to the x and x plus 3, you should be able to get a quick sketch of those by hand, which sometimes you won't be able to get a quick sketch by hand because it'll be kind of complicated equations. But in this case, e to the x looks like this, and x plus 3 looks kind of like that. Not the greatest graph, but if you're having a tough time with this, you could graph that in your calculator. But again, both of those are graphs that you should be able to get an idea what those look like. So again, this y equals x plus 3 is the straight line, y equals e to the x is the exponential graph we have right there. So we're trying to find this area right here that's bounded by these two graphs. Okay, that's the area we're looking for. So, this is going to just be the integral of the top curve, which is x plus 3, minus the bottom curve, which is e to the x. And to set up our limits of integration, we need to find our intersection points. Well, last time here, we just set them equal to each other and solved by hand. In this case, that's going to be a bit more difficult because solving e to the x equals x plus 3 would be kind of difficult. So we're going to go ahead and use our calculator to find our intersection points. So, in y1, you're going to have e to the x. In y2, you're going to have x plus 3. And if you need to pause this, as you go through, that's fine. So once you do so, you're going to graph both of those equations, and you should, you have to be in a window that you can see both of these and see this intersection area here. And then you're going to press second calc. You're going to scroll down to intersect, which is number 5. Press enter. It asks you to identify the first and second curve. Well, there's only 2 curves on the screen, so just press enter for each one. And then it says to guess. Well, there are 2 intersection points, so the guess just means which one are you looking for right now, basically. So let's say we'll look for this one first. If I look on my calculator, that looks to be around maybe x equals -2. So what I'm going to do is I'm just going to type in -2 and press enter. And it will tell me, okay, I was a little off. It's actually at -2.9475. Okay, got to always go to at least 3 decimal places. And I'm going to press second calc intersect again to find my other one. And if I look in my calculator after I do my first and second curve, it looks like that's, oh gosh, maybe a little after x equals 1. So if I type in 1 and press enter for my guess, it will tell me the intersection that's kind of close to 1, which is 1.505. So there are my limits of integration, -2.9475 and 1.505. Now I want to integrate this, and I'm going to use my calculator to do so. Common mistake. Okay, currently in your calculator you probably have in y1 e to the x, and y2 you have x plus 3. I've seen many people just from that point press second calc integrate in order to evaluate this integral. Make sure that this is what is typed in. So you're going to have to go back, and like I will clear out of y2, and I'll clear out of y1 as well, how about? So in y1, I'm going to put this equation in. If this is what I want to integrate, that is the equation that needs to be there. So it's going to be x plus 3 minus e to the x. That's, this is what needs to be written in y1. And then after I, graph this, I can then go ahead and integrate it by doing my second calc integral, typing in my lower limit first here of -2.9475 0.9475, typing my upper limit of 1.505, and I end up getting 5.694. So that number right there represents the area of that shaded region.